Welcome and hello. This is a support video in HEC RAS, and in this video I've titled it Subcritical Flow versus Supercritical Flow. That is one of the issues in the model that I'm going to discuss. This is a model review, so there's a few other points I'm going to point out first. I was asked to review a model and just double check that the results looked correct. And what we're looking at here is a single river, single reach. This is a bridge. I'll bring the bridge details up right here. If I click on deck/roadway, what we have in these numbers shows a 60-foot wide span in the bridge opening for the water to flow through. And in a different model, this is one alternative. A second alternative has a 44 meter, sorry, we're dealing with meters here. This is a metric model. So this one is 60 meters wide, and then the other model has a 44 meter wide span opening to convey the flow underneath the bridge. So what I'm asked to do is double check these numbers and make sure that the flow velocities, depth, and water surface elevation is as the original modeler thinks they are when they sent me these files. All right. The first comment I wanted to make was, first of all, I was sent two different project files. So if I go up to geometry, file, open geometry data, I'll click yes. There's only one geometry file in this project file. This is the 60-meter wide bridge opening geometry. What I was also sent is a 44-meter wide span opening. Here's that model. Basically the exact same model. Here is the bridge. Here is the deck/roadway data. And then right here, these two rows here is where the low chord is much higher, representing the, 44 meters between these two cross-section stations. So my first advice would just be to create both of these geometries in the same project file. There's no reason to separate them into separate project files, at least nothing that's obvious to me, because if I open up the geometry, boom, here's the only geometry. So what you could have is a geometry that says 44-meter wide and bridge opening or something like that, and the other geometry could say 60-meter wide. That way you're not duplicating all the flow data, you're not duplicating all the other geometry data. When the only thing you need to really change is the bridge deck/roadway data. The second point I wanted to make before we actually get to the flow regime of subcritical and supercritical is if we open up the cross-section data right here, this geometry here is incredibly steep. So if I go to plot profile, what we're seeing here is somewhere in the neighborhood of a 10 to 12% longitudinal slope in the river. And I don't know what model this is. I suppose that's possible. Typically, you're going to be seeing slopes more in the neighborhood of 0.1% up to 1%. So when I saw these numbers and it said 10%, I just wanted to double check with the modeler that that is correct for your river geometry. So you could just go ahead and do a quick rise over run calculation, either in this view here, or you could look at the numbers right here. Actually, what you do is get the invert elevation of the first cross section, the most downstream cross section, and then go up to the next river station and then use the distance between. So the distance between is 50 meters. And what I calculated was the rise is a little bit more than 5 meters. So indeed, it was closer to 11 or 12% longitudinal slope, which is what we're seeing when we plot the profile. Okay. So anyway, I just wanted to double check that that was a little bit suspicious, but not necessarily wrong. In fact, one recommendation I would make, since this is only a few hundred meters, is to extend the river reach further upstream and downstream if indeed this is a critical section with a bridge that has an absurdly steep slope. So what tipped me off to this was when I looked at the hydraulic data, which we have right here. We have 3 profiles and a steady flow data profile. Q25, Q50, and Q100 for the return flow rates. And then if you click on boundary conditions, we're using normal depth for 12%. So that is also very steep, but it is consistent with the geometry. So that looks good. All right, finally getting to what this video is titled, the flow regime. If I go up to run and then steady flow analysis, the flow regime here is set to subcritical, and with such a steep slope, that's probably not the case, but let's go ahead and run the model anyway and see what happens. Again, this is the model with a 44-meter wide bridge span opening. Next, what I'm going to do is click on View Profile Summary Table, and then click on Standard Table 1. And all of our food numbers, except for just upstream of the bridge, is right at 1. So this is, to me, is suspicious. If your food number is 1 or near 1, like 1.01 or 0.99, probably means you selected the wrong flow regime. So let's just go ahead and select supercritical or even mixed now, because both boundary conditions are defined. I'll go ahead and select mixed and then click on compute. Let that run. I'm going to look at the exact same table we were looking at before. I'll go up to view, profile summary table. Now our food number is way up here at 2.7, 2.54, 2.62. I am focusing in on Q50, which has a flow rate of 256.6 meters cubed per second. But anyway, this makes me believe that indeed we have supercritical flow. What I also did is I went up to the 6 cross-section bridge standard table, and then I added a couple additional columns, save that user table as T1. So I also have the hydraulic depth and the max channel depth, because these were some of the numbers that the original modeler sent me to check: 4.28, 1.36, and 1.62 with a water surface elevation of 1576.58. So what I'm going to do now is just hop over to the other model, which uses the 60-meter wide bridge span opening. So open a new model. Usually you just be switching to a different plan that uses a different geometry, but I've already mentioned that. Okay, so let's go ahead and now run the supercritical version, because this model had the exact same issue. Click on compute. All right, so that ran. I'll click on close, and now let's view the profile summary table. Again, this is my custom T1 table, and for the flow rate of Q50, we're now looking at a water surface elevation of 1576.29, and that's meters. And then here is our average channel velocity, hydraulic depth, and maximum channel depth. So to compare the results, this is supercritical flow, not subcritical flow. The first bunch of numbers here is for the 44-meter wide bridge span opening. The second group of numbers is for the original 60-meter wide bridge span opening. For the 60-meter wide opening, the water surface elevation for that design flow rate of 50-year return period is 1576.29. And if we reduce that bridge opening down to 44 meters, the water surface elevation increases to 1576.58. So it's an increase of about 0.29 meters, which is about 1 foot, which is not a whole lot. The flow area decreases a little bit. We can just tell by the decrease in flow velocity, because it's a constant flow rate between both of these two model runs. The hydraulic depth is a little bit larger, and the max channel depth is also a little bit larger compared to the 60-meter wide span bridge opening scenario. Now, we didn't see a very large increase in water surface elevation or depth when decreasing the span from 60 meters down to 44 meters. I think that's partially because the slope of the channel is set to 12%, which is very large. So if the slope is not 12%, then we could very well be seeing larger increases in that water surface and depth numbers when decreasing the span width through the bridge. All right, so anyway, I hope that was helpful. A couple things I would check again is check your geometry, make sure it really is 12% grade. And then also make sure you're using the correct flow regime, either supercritical, subcritical, or if you're not sure, you can click on mixed. What I'll also do is check that food number to make sure it's not right at 1, because whenever I see that, it makes me think that I selected the wrong flow regime. All right, hope that was helpful.